All right, time for the second video on covalent bonding. This time we're going to go all the way through the nomenclature. So we'll do the Lewis structures, we'll do the structural formulas as part of polarity, and we'll add to it that whole polarity concept, as well as an understanding of the rules for binary covalent nomenclature. So we're going to start off with this compound, PCl3. Take a look at the whole process, every step of the way. Look at what its structure looks like, what its polarity looks like, what its negatives and all that. But we're going to approach it like we did in class today, as we're going to do on a quiz tomorrow, from the polarity aspect. PCl3, we want to know if this molecule is polar or not. And the first thing we're going to have to do in that process is analyze the bond between phosphorus and chlorine. Phosphorus has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. The difference between those two, 0.9. As we talked about in class, if you're looking at an electronegativity of 0.5 or higher, what you're looking at is indeed a polar bond. Now, as I said in class, if you identify that bond as being nonpolar, then automatically your molecule is going to be nonpolar. Polar means charges. And if you don't have charges in the bond, there's no way you can have charges in the molecule itself. If you come up with a polar bond, then you have to take it to the next step. You've got to look at the structural formula. You have to look for separation of charge. So, carrying on into the Lewis structure and the structural formula. Phosphorus is in group 5A, so it has 5 valence electrons. 1, 2, 3, 4, 5. Chlorine is in group 7A, so it has 7 valence electrons. 1, 2, 3, 4, 5, 6, and 7. The one that has the most single dots can make the most bonds. The one that has the most single dots will be the center atom in your structure. So as you draw it, start with the phosphorus first. Connect the 3 chlorines to the single dots. Rotate the Lewis structure for the chlorine so that its single dot lines up with a single dot in the phosphorus. You end up with something that looks like that. Now, to go to the structural formula, we have to look at the middle atom. We have to look at this phosphorus and see if we shared all its electrons. We did not. We have a pair of unshared electrons in the phosphorus. 1, 2, 3, 4 atoms with unshared electrons is pyramidal. To draw a pyramidal, start with your center atom and arrange the other ones below it. This two-dimensional drawing represents a three-dimensional shape. This thing looks like a tiny little pyramid, or the legs on a tripod. Now we have to talk charge. We have to go back to this. The one with the lower electronegativity is going to be positive. The one with the higher electronegativity is going to be negative. So everywhere we see a phosphorus, we put a positive charge. Everywhere we see a chlorine, we put a negative charge. And we ask ourselves, can we draw a straight line through that molecule? Put all the positives on one side, all the negatives on the other? And we can. We can draw a horizontal line through that molecule. Have the positive on one side, all the negatives on the other. If we can do that, then what we are looking at is a polar molecule. So PCl3 is indeed a polar molecule. So again, it starts with the polar bonds. You have to have a polar bond in order to have a polar molecule. But more importantly, you have to have separation of charge. That's where you have to draw the Lewis structures, model the bonding, draw the structural formula, and look for that separation of charge. Now let's talk nomenclature, because we can't just call this thing PCl3. That's like spelling your name. Nobody walks up to you and says, "Hello, John." They call you by your name. So this has a name. The name is based on prefixes. These prefixes are attached to the subscripts in that particular formula. Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and so on. The rules are, you can't use mono on the first element, so if there's just one of them, you would just write down the name of that particular element. If there's 2, 3, or 4, or 5, you can use a prefix. Just no mono on the first one. Change the ending of the second one to IDE. And kind of be careful with those oxygen ones. Most of the time we drop the O's and the A's from the prefixes before we stick them on oxygen to reduce the number of vowels and make it sound a little bit better. So let's take a look at this one. There's no subscript on the phosphorus, so we assume it's 1. The prefix for 1 is mono, but we're not allowed to use that. So we just write phosphorus. Move on to the chlorine. 3. The prefix for 3 is tri. Here we have to change the ending. So chlorine becomes chloride. Again, no mono on the first one. You can use anything else. Change the second one to IDE. Let's take a look at this one. Well, let's get that one. Let's go to this one. BN. Again, it starts with looking for the polarity. Boron has an electronegativity of 2.0. Nitrogen has an electronegativity of 3.0. The difference is 1.0. And again, 0.5 or higher will make a polar bond. So this is a polar bond. Like I said, if you say nonpolar here, you automatically have a nonpolar molecule. But if you say polar, you have to continue on with the structural formulas, the separation of charge, all of that. So we said polar, we got to work on. We have to draw the Lewis structure for boron. Boron is in group 3A, so it has 3 valence electrons. We draw the Lewis structure for nitrogen. Nitrogen's in group 5A, so 5 valence electrons. 1, 2, 3, 4, 5. They both have 3 dots. And we normally would say the one that has the most dots, the most single dots, has the center atom, but in this case they're both the same. Doesn't matter which one we draw first. Not going to matter anyways because it's just BN. There's just 2 atoms, so there really is no center to worry about. So draw the boron. Draw the nitrogen, rotating it, moving the double dots over to the right-hand side so the single dots will line up better. You can circle them out. That's what the covalent bonding looks like. Now, it's really not that important, this one, other than to tell us that it's got a triple bond. We've circled 3 sets. We have a triple bond. It's going to be linear. There's no other shape it could be. 2-atom molecules are always linear. We just have to know how many sticks to draw between the 2 atoms. In this case, we're going to draw 3 of them, again, because we circled 3 sets of electrons. Now for charge. The lower number 1 is positive. The higher number is negative. So where we see the B, we put a plus sign. Where we see the N, we put a minus sign. And we ask ourselves, can we split those with a straight line? And we can, a straight line going up and down. It's all the positive on one side, all the negative on the other. This is a polar molecule. And as I told you in class the other day, if it's a 2-atom molecule, if it has polar bonds, it's going to be a polar molecule because you'll always be able to split them when there's just 2 atoms. Nomenclature-wise, again, it's all about the prefixes. Neither one of these has a prefix on it, so we're going to make the assumption of 1. We're not allowed to use mono on the first element, but we are allowed to use it on the second one. Remember, you don't change the name of the first element, so it's just boron. Again, don't put mono on it because you're not allowed to use mono on the first one. For the second one, you are. Change nitrogen to nitride. So you're going to prefix that tells you what the subscript was, IDE ending on the second element. Don't ever use mono on the first one. Sulfur and oxygen. Again, we got to start by doing the electronegativity differences. Sulfur is a 2.5. Oxygen is a 3.5. An electronegativity difference of 1.0. And again, if it's over 0.5, it's polar. So we do have polar bonds. The sulfur-oxygen bonds are polar. And again, whenever the bonds are polar, we have to go a step further and figure out if the molecule is polar. Let's draw out the structures for this. And as I do so, I realize this is one that I didn't really want you to do. This probably should have been silicon instead of sulfur there, in which case we would have the 4 bonds in this. This is probably a typo. Rather than start over, I'm just going to fix the typo. That was probably supposed to be silicon dioxide, not sulfur dioxide. Silicon is what that probably should have been. Silicon is something we can work with. I never taught you how to deal with that sulfur one because we didn't do any type of bonding with the simple straight up valence stuff. Silicon's 1.8. Oxygen is 3.5. So again, we're still in that polarity range. We're definitely over the 0.5. Here we have a difference of 1.7. Again, over 0.5 is polar. So just like before, we have polar bonds. Now, fluid structures we can actually work with. Silicon, group 4A has 4 valence electrons. Oxygen, 6A has 6 valence electrons. The one that has the most single dots is the one that goes in the middle. So start with that. Rotate your oxygen structure so the single dots are facing the silicon. Makes it easier for us to do the bonding. Over here, I'll rotate it the other way. Again, to make it easier to do the bonding. These pairs have to stay adjacent. The singles have to stay adjacent. You can't split it up. Don't ever put the pairs on opposite sides. Keep them the way they show up in the original Lewis structure. Now we've got a 3-atom molecule. We look at the center atom. We have used up all its dots, so this is 3 atoms, no unshared electrons. It's a linear molecule. When we attach the oxygens and the silicons, we're going to use 2 dashes because we've circled 2 sets of electrons between each one. So this is double bonded. Again, linear molecule because there are no unshared electrons. We used up all the sulfur's electrons. Double bonded because we circled 2 pairs of electrons between each one. Now for the charge. We go back and assign charges. Lower one is positive, higher one is negative. So where we see a silicon, we put a plus sign. Where we see the oxygen, we put the negative sign. We ask ourselves, can we draw a straight line through this and put all the positives on one side, all the negatives on the other? This time the answer is no. There is no way you can draw a line through this that's going to put the positive on one side and both negatives on the other side. So this is a nonpolar. On to the nomenclature. No subscript on the silicon, so we assume it's 1. Can't use mono on it, so it's just silicon. Prefix for 2 is di. Oxygen changes to oxide. The I's usually stick on the prefixes when we're attaching it to oxygen. O's and A's most of the time are dropped. So if it had been mono, we'd drop the O off the end of mono and call it monoxide. If it had been tetra, we'd drop the A off the end and call it tetroxide. But the I's stick around, so di remains di. One more, CH4. Again, it all starts by analyzing the electronegativity. Carbon is a 2.5, hydrogen is a 2.1. The electronegativity difference of 0.4, this is nonpolar. We have nonpolar bonds. Again, we need to be 0.5 or higher to have polarity in the bonds. 0.4 doesn't cut it, so it's nonpolar bonds. And again, automatically, this is a nonpolar molecule. We don't have to go through the drawings. We don't have to look at the structures. If the bonds aren't polar, the molecule is not polar. Name-wise, this is a little weird. This comes from the realm of organic chemistry. This is not carbon tetrahydride. CH4 is one of those organic compounds, the primary component of natural gas. We call it methane. So this is one of those exceptions I told you about that don't follow the rules for binary nomenclature.